Okay, so good afternoon. Hello, can you guys hear me?
Good afternoon, sir.
All right, so that's good. Okay, so last meeting we have just finished to up to this point, inverting amplifier. Okay, so are you guys ready now to have a discussion on the next topic that you're going to do with your laboratory? Are you guys now ready? Or
Sir.
Yes, sir.
Yes, sir.
you guys have any concerns or question before we continue this discussion? All right, so I guess none. So the next one is differential amplifier. Okay. So in differential amplifier, so we also have two rules, which is kind of the same with inverting amplifier. So no current flows in or out of the inputs. So what are those inputs? Right here at this point, V sub A and then V sub B. If you're going to measure this one on the LT spice, you will read nothing. Yes, in 0 volts. And then the second rule here is the op amp tries to keep the inputs the same voltage, which is, for example, your input here in V sub 2 is this voltage. It will try to equalize that one on our second input. Okay, so that is why V plus is equal to V minus. So whatever is also the input of your IR1, so you can see right here, this one is your IR1, is equal to your current on the IR. Okay? The same with the IR2. Whatever is the current on this resistor will be your current also on the IRG. But then again, so you're going to take a look on this one. We don't have any currents that flows in these two inputs, V sub E and then V sub B. So it's like a magic. So if you're going to take a look on this one is not connected on this V out anymore. Okay, so for some reason, the current is like jumping on our V sub out. Same with our V sub 1. So at this point, okay, of course, since we have a loop here, then that's obvious that this current will flow to our V sub out. And if you're going to take a look on this one, we have this node and then node here also. Those are the things that we call virtual ground. Okay, so that is why if we have a current here, it also passes on the other grounded area. Okay, so that is why we call that one a virtual ground. Okay, so this is a standard operation amplifier which has 2 points, inverting and then non-inverting. So we can also connect signals to both of these inputs at the same time, producing another common type of operational amplifier circuit called a differential amplifier. So last meeting we have discussed one input only, which is an inverting or non-inverting. But once you have two inputs, like for example this one, so input on the inverting and then another input on your non-inverting, this one now is called differential amplifier. Okay. Okay, so let's have an example of this differential amplifier. So we have this scenario when the resistors R1 is equal to R2, sorry, and then R3 is equal to R4. The diagram on the right for the differential amplifier can be simplified to the following expression. So if ever that this R1 is equal to this R2, and then R3 is equal to R4, then we could say that this one can be simplified using this formula, which is V out is equal to R3 divided by R1 times V2 minus V1. Okay, so it's very simple. If you have the same values for R1 and R2, same with R3 and R4. However, if you have different values, okay, like R1, this one. If we have R1, okay, which is not equal to your R2, and then R3, which is not also equal with your R4, you'll have to use this one, which is a more complicated formula. Okay. But for now, we will discuss the common or the same resistor. So we will go back on that one later. So let's have this example for differential amplifier wherein they have the same values of resistance. So we have here a given wherein R1 is equal to R2, wherein their values is 9K, and then R3 is equal to R4. wherein the values of those two resistors are 1K. And then for V1, it's 2 volts, and then for V2, it's 3 volts. So the question here is find V out. Okay, so just simply use this formula, okay, which is now this one, and then just simply substitute the corresponding values. So R3 is 1K, and then R1 is 9K. So 1K divided by 9K times. So your V2 here is 3 volts, and then your V1 here is 2 volts. Okay, so just simplify this one, and then you will get 9 volts. Okay. Oops. R3 is 1K divided by 9K. Is this correct? 1K divided by 1 over 9. 3 minus 2, 1. Looks like this one is wrong. Wait, let me correct this one. R3 divided by R1. R3 divided by R1. R3 is 9K. Sorry. So this one is 1K. And then this one is 9K. Okay. So it's the opposite. So our reference voltage is always higher than our series resistance in here, or our input resistance. So R3 and R4 is 9K, and then R1 and R2 is 1K. So that is why this one should be 9K divided by 1K. Okay. So sorry for that one. And then just simplify this one, and then you will get 9 volts. So did you guys get this one so far? So in differential amplifier, so we're actually getting their individual voltages. So for example, the voltage computed in your inverting amplifier, and then the voltage that is passing the non-inverting amplifier. So you can actually get their values one by one, like what we did in the non-inverting and then the inverting computation, and then just combine those two. Okay, but since we can use this simpler formula, then we will use this one instead. But you can also do the longer method, which is applying the non-inverting solo and then the inverting solo. Okay. So how do you do that? How do you do that one? So if you're going to solve for V1 and you're going to get the V out, so you have to ground this one first. Okay. So the same with the other one. So if you're going to get the voltage output of this V sub 2, you have to ground this V sub 1 also. Or just by simply making this voltage 1 equal to 0. Okay. But then again, since we can use this, simplified or more simpler formula, then that's the one that we're going to use. Right? So did you guys get this one or no? Hello? Can you guys hear me? Are you guys still there?
Yes, sir.
Yes, sir.
So how is it going for the differential amplifier? Can you guys follow or no?
We can follow, sir.
That's good. Okay. So I hope all of you can really follow. Well, if ever that you have a question or clarification, so feel free to ask me anything. Okay. So yeah, that's it for the differential amplifier, and then having same resistance value for R1 and R2, and then R3 and R4. Okay. So maybe the next thing that you want to do is verify this one in the LTSpice, whether this one is really correct or no. Okay, so let's do this one in LTSpice. So I'll just create a new schematic. So we're going to use op-amp, universal op-amp. Okay. And then we need 4 resistors. So this is for the reference voltage of the inverting, and then the reference voltage for the non-inverting. And then to another input resistance for the R1 and R2. And then 2 voltages for the non-inverting and then the inverting inputs. And then another 2 voltage, okay, for the rail voltages, which is this one, okay? Then all we need to do is connect them using wires. Okay, so this is our reference voltage. And then this is our R1. So I'll just arrange this one like that. Maybe you guys cannot see this one. I'll just put it here. There you go. And then you can just simply put here ground. And then for the second input, for the non-inverting, so we have here the reference voltage, which is also connected to ground. And then the another Rin, which is now connected to your inputs, or input number 2. All right, so another wire here and then another wire here. So our R3 and R4 is 9K, and then R1 and R2 is 1K. Okay. So this one is 1K, this one is also 1K, this one is 9K, and then this one is also 9K. And then I'll just change the variable names. R1, R2, R3, R4. We have the same R1, R2, R3, R4. R1, R2, R3, R4. Okay, that's good. And then we have here the rail voltages. So we have here the positive supply and then the negative supply. And then connect this one into ground also. And then this one is 2 volts, and then the other one is 3 volts. So V1 is 2 volts, and then the other one is 3 volts. Okay. What else? All right, so I guess we are already done. So that's it for the schematic. So let's now try to simulate. So just click run, and then we'll simulate this one in 50 milliseconds. Oh, I guess there is an error. Sorry. So I forgot to put the voltages for our rail voltage. So I'll just put here positive 20 volts and then negative 20 volts. And then what else? Oops. And then we forgot to put the ground in here. Okay. So I guess that's it. So there you go. So right now I've just measured the V out, okay, wherein our reading is 9 volts. I guess it's no, it's not really 9 volts, it's 8.999. So just like last time. It's not exactly 9 volts, but at least super close to 9 volts. Okay. Wherein our result in here is 9 volts. Okay. So as you can see, they are just the same. So you can actually test this one using an LT spice. All right. So that's it for the same values for R1 and R2. And then the next one is having a different values for your R1, R2, R3, and then R4. Okay. So if this is a scenario and we still have the same diagram, then we can apply or we can solve the V out by applying this formula. So it's quite longer since you have different values for your resistors. So again, how did we come up with this kind of formula? So we have these derivations on the link that is included on our module. Okay. if ever that you wanted to know how they come up with such a formula. Okay, so let's have an example for this one. So in here, I've just set a different random values. So we have here 90 for R1, 3K for R2, and then R3 is 1K, and then R4 is 4K. Okay. So same voltages input, which is 2 volts and then 3 volts, and then same question. So find V out. So all we need to do is get that formula and then replace their corresponding values. And then once you have, say, calculated the final result, then you will arrive at 1.68 volts. Okay. So let's see if we have the same values if we're going to do this one in LT Spice. So do not analyze this one for now. So just analyze this one once our discussion is done. So I'm just showing to you guys that this is an example in actual, and then this is how to do that one in LT Spice. So 9K for R1, and then R2 is 3K, and then R3 is 1K, R4 is 4K, and V1, V2, 2 volts, and then 3 volts, and then find V out. So let's see. So there you go. We have here 1.68, okay, which is super the same with our actual result in this example. Okay. So were you guys able to follow?
Yes, sir.
So just verify this one later, okay, once we're done with our discussion. So for now, just take a look on this one that this is the substitute values for the corresponding formulas. Okay, and then we arrive at the result of 1.68 volts. Right? And then we have another one, which is summing amplifier. So if we have deduction, okay, we also have summing or summation. Okay. So in summation, our inputs are in inverting amplifier, which will make our result negative. Okay. But the one that we're trying to make work in here is the voltages that is being input to our inverting input. So V1, V2, and then V3 should add up and then should arrive with a single output. So the summing amplifier is another type of operational amplifier circuit configuration that is used to combine the voltages present on two or more inputs into a single output voltage, as what its name trying to imply, summing the voltages and then making it into a single output. So if we add more inputs resistors to the input, each equal in value to the original input resistor, which is the Rin, we end up with another operational amplifier circuit, which is called the summing amplifier, okay, or the summing inverter, or this voltage adder. So it has a lot of names, but the most common name of this one is summing amplifier, okay, which is also shown on the right side. Okay, so this one is very simple. So if ever that you're going to remove V2 and V3, this one is already an inverting amplifier. But since we have additional two inputs, okay, which also has additional two resistor inputs, this one now is making the or composing the summing amplifier. Okay, and then your non-inverting input is grounded. Okay, so for you to appreciate this one, so let's have an example. So we have these derivations. If you want to get the single currents on each of those nodes, so for example, this one or this path, so you can get this one by getting the V1 divided by Rin, or R1 rather. Or if you want to get the I2, so V2 divided by R2, or if you want to get the I3, which is V3 divided by R3. Or if you want to get the total current, which is the IF now, right here, so you can just simply add all of those currents. Okay? So again, just going back to the inverting equation. So in solving the V out for inverting equation, so you have to get the negative sign, okay, or basically just invert or negate the sign of your inputs. So if you have positive, then that one will become a negative. If we have negative, then that one will become positive. So in here, since we have positive inputs, then all we have to do is negate the entire formula. So negative RF divided by R in times V in. Okay. Well, this one is if you only have a single input. But if you have 3 inputs, then you have to use this one now. Okay. Which is basically came from the inverting equation, which is negative V out is equal to RF divided by R in times V1. So this is for the first line, this one. And then the second one is RF divided by R in plus, times V2. And then the last one is RF divided by R in times V3. So as you can see, we have patterns which can be simplified into, like this. Okay. So you can bring out the V1 and then have RF divided by R1 plus V2 divided by, times RF divided by R2, and so on and so forth. And then by simplifying this one further, you can actually arrive into a simpler formula, which we have in here right now. So RF times V1 divided by R1 plus V2 divided by R2 plus V3 divided by R3. Okay. And then it says here, etc. if ever that you have 3 or more inputs. Okay. So in summing amplifier, so you can have 2 inputs or 3 inputs or 4 inputs or more than. Okay. If there is only 1 input, then that is not summing amplifier anymore. That one is just an inverting amplifier. Okay. So were you guys able to follow on how we've come up with this formula? The last one, this one. Yes, sir, coming from Mr. Domain. Okay, how about the others? So you can use your mic. So don't be shy to speak. Okay? You guys have beautiful voices. So you have to maximize your resources para hindi mas nakakapagod, di ba? Mas nakakapagod mag-type. Anyway, so if you guys do not have a question anymore, then let's now proceed to the example. Okay, so we have here scaling summing amplifier. So find V out. Okay, so the given is already in here. So we have the R1, which is 1K, and then the R2 is 2K, and then the reference voltage is 10K, and then 2 millivolts for the first input, and then 5 millivolts for the second input. Okay, so in here, all we need to do is get this one, and then put it here. And since, as you can see, we don't have voltage 3 and then R3, then we'll just have to put 2 voltages and then 2 resistors also. So from negative V out, it will become negative. So we want to transfer that negative into the right side. So what is the value of RF? So it's 10K times your V1 is 2 millivolts divided by 1K. And then for the second one is 5 millivolts divided by 2K. So if you're going to solve this one, you'll arrive at a result of negative 45 millivolts. So as you can see, you have positive inputs and then it's just simply inverted, okay, or it was just simply negated, okay. So from positive, it became negative. So let's see if we have the same results in using LT Spice. So what are the things that we have to change? So we can just remove this one. And this one is grounded. Yeah. Grounded. And then another voltage for another input. And then another resistor for another resistor inputs. And then this one is also connected to ground. Oops. 9. There you go. So V1 is 2 millivolts, and then V2 is 5 millivolts. So 2 millivolts, and then 5 millivolts. Right? And then 1K, 2K, 10K. 1K, 2K, 10K. 1K, 2K, 10K. Right? And then I will not make changes on our rail voltages. So again, take note, these rail voltages are just our limitation when it comes to measuring this V out. So our maximum positive voltage is 20 volts, and then our maximum negative voltage is negative 20. Right? So let's see if we can have the same results. So there you go. So as you can see, we have negative 45, which is, or actually negative 44.99, which is super close with our result in here. Okay. Gets or no?
Gets, sir, gets.
Okay. That's plus. Okay. So it seems that most of you get it perfectly. Anyway, so this is the second type of summing amplifier wherein Rin is equal in values. So meaning your Rin or your R1, R2, and R3 are the same, or they have the same values. Okay. So if ever that is the case, then we can just simply use this formula. So this one is much more simpler when it comes to having a same values of Rin. So negative V out is equal to Rf divided by Rin times V1 plus V2 plus V3. Okay. And then of course you want to transfer this negative on the right side. So again, your positive inputs will become negative input, or vice versa. Your negative inputs will become positive output. Okay, so let's have this example. So we have here a given wherein Rin is 20K. So all of them are 20K. And then your Rf is 20K also. And then V1, V2, V3 is 2 volts, 3 volts, and then 5 volts. So here the question here is find V out. So here's the solution. So again, where this one came from? From our simplified formula of summing amplifier. Okay, so just copy that one and then paste it here. And then just replace their corresponding variables into their corresponding values. So Rf is 20K, and then Rin is 20K, and then V1 is 2 volts, and then V2 is 3 volts, and then V3 is 5 volts. So if you're going to simplify this one, so you can start here or start here, so anywhere. So I want to start here. So 2 plus 3 plus 5 is 10. And then if you're going to simplify this one, so 20K divided by 20K is 1. So 10 times 1 is positive 10. And then just simply negate that 1. So that is why we now have negative 10 volts. Did you guys get it? Okay, yes, sir. Coming from Mr. Martinez. Yes, sir. Coming from Mr. Zenizal. How about the others? Did you guys get it or no? Am I too fast?
Ito lang, sir.
No, sir, no.
Sakto lang.
Sakto lang, sir.
Okay, that's good then. Okay, so that's it for your additional laboratories. Okay, so again, so here are the links where I've got those topics. And then here's your additional laboratory. Okay, so this one is laboratory 4, 5, 6, and 7. So 4 and 5 is differential amplifier. And then 6 and 7 is for summing amplifier. Okay. So I will leave the analyzation part into you guys. I have already shown to you on how to, come up with such, call this one, circuit diagram. Okay, so in here, we've just, copy this one into the same, but just at different values. So the same with number 5. And then for number 6, So before we only have 2 inputs, but in here we now have 3 inputs. Okay, and then just follow the basic configurations that I put in here, and then make sure that you have done it properly without missing any step, so that you can arrive with the same correct answer as I have on my notes that I have saved. Okay, so 4 and 5 is differential amplifier, and then 6 and 7 is summing amplifier. So 6 and 7. So yeah, basically this one is the scaling summing amplifier, wherein we have different values, and then summing amplifier Rin is equal, wherein our resistor inputs are equal. And then for number 4, this one is having the same values for some resistors like what we have discussed, which is R1 is equal to R2, and then R3 is equal to R4. And then for number 5, this one is having different values on all of the resistors. Okay, so the same instruction as before. So you're going to take a screenshot of your schematic and then the screenshot of your graph of the voltage output. So all of them have the same question. So screenshot of your schematic and then screenshot of your V out result. So Sir Duman. So Duman has a question. Sir, anong op-amp gagamitin? Universal. So the one that you're going to use is, I think I have indicated it in here. Wala nga. All right. So
Meron,
the
sir, doon sa may kwan.
that you're going to use for number 4 and number 5 is universal op-amp. Okay. So there you go. I have just included that use universal op-amp. Okay. So same with number 6 and number 7. Right? So yeah, that's it for your 4th, 5th, 6th, and 7th laboratories. So any question or concern so far?
Sir, ako po.
Mhm.
Yung sa LM741 po sa past activity nga eh.
Mhm.
Pag iraran mo po siya ang sabi port pin mismatch. Mas mataas daw po yung instance nung sa may positive kesa dun sa ano.
So have you checked the polarities? So in here, I actually have an input for my rail voltage, which is positive going to negative, but I've changed the polarity or the sign rather of my voltage, which is negative. So you can actually put here just 20, but we have to make this into like this, wherein they are just the same. So this one now is negative 20 volts. So check this one. So most of us having troubles are on our rail voltages. Okay,
Ay, sir.
check this one. Okay, and what else? I guess that's the only part that you're going to have an error. And then the rest, if ever that you miss putting any values, I guess you will not get any error. Okay. So any other concern or question? When did I? Oh yeah. So the deadline of your lab 1, 2, and 3 will be on this coming Thursday, right? So to those who haven't finished lab 1, 2, and 3 yet, so make sure to finish them before the deadline. Okay. And then what else? I guess that's it. So we will just discuss the following topics next meeting. And then of course, we're going to have new laboratories again. Okay. So yeah, you have a lot of laboratories, but they are just super easy and super simple. Okay. They are just super similar with the one that we have discussed on our module. All right, so yeah, that's it. So if you guys do not have a question anymore, so you guys may now go. And then thank you for attending on our Zoom meeting. I really appreciate it.
Bye, sir.
Thank you, sir.
Sir,
Bye.
thank you.
Thank you.
Thank you, sir. Bye.
Goodbye.
Thank you, sir.
Thank you too. Alright. Okay, so dito nag-work mic ni Mr. Sarmiento. Bili ka na ng bagong mic.